Hi, my name is Lizzie Stasenko, and I'm a sophomore at UNC, pretty much a rising junior at this point. And I'm a bio major, and I'm super excited to apply for peer mentoring next fall. I actually applied last year and was selected, but unfortunately couldn't do it because of class conflicts. And so I'm super excited to do it again this year. I'm applying to peer mentor for Orgo 1, but the reason I want to peer mentor in general is because I felt like after going through Gen Chem 1 and 2 and Orgo 1 and 2, the peer mentors were crucial to me doing really, really well in the class, by whether it was just like being available in class to ask questions or going to their review sessions. It was a great resource for me to like actively learn. And after taking Orgo 1 and feeling like I succeeded really well in the class by understanding material like conceptually on a pretty high level, I would love to be that same resource for other students, whether they're struggling or they just want extra practice. And especially with like Orgo 1, in the middle of the class, I kind of struggled a bit, which was reflected on my second exam score. But after utilizing the resources I had, such as the peer mentors, I was able to do much better and almost get a perfect score on the third exam. So after mastering all this material, I would love to be a resource for students, both like by helping them academically and like helping them grow as students. So I chose a problem from midterm 3, about like SN1, SN2, E1, E2 reaction mechanisms. And this is a synthesis problem. So when I'm working with any synthesis problems, I start out by looking at the reactants and the products and looking for any clues to what happened in between. So here, the one big clue I found were these two oxygens separated by two carbons, and they're anti to one another. So that means there's an epoxide involved somewhere in the middle here. And looking at our reactants, there's no alkene to get an epoxide attached to this side. So I knew I had to somehow form an alkene here first. And I did this through an E2 mechanism, since even though we can do E1 since it's a tertiary carbon or tertiary alkyl halide, E2 is just easier when you have strong base. So, because you don't need heat. So I added strong base to deprotonate. I'll use my little pointer to deprotonate this H right here, which in turn, this bond formed the alkene right here, and then the Br acted as a leaving group. So we ended up with this product, and now we have the alkene, which will react with MCPBA to form an epoxide. So we don't have to know the mechanism here, or at least we didn't in the fall. And so you get an epoxides form syn with the O syn. So now that we created our epoxide, we have to figure out how to open it to get this final product right here. So as you can see, the nucleophile added to the less substituted side. So this means that this attack occurred in basic conditions. If the nucleophile added to this side of the epoxide, that would mean it was in acidic conditions. The epoxide adds to the less substituted side in basic conditions because since the reaction is so favorable when you have the negative charge on the strong base right here, sterics come into play more, so it adds to the less substituted side. So the base in this situation is the epoxide, and it reacts with this carbon electrophile right here. I'll show it on this molecule, and then this bond goes up here. The electrons in this bond go up pyrimine, and then this adds over here. And it adds anti to the oxygen, to the bridged oxygen intermediate, because the nucleophile can only attack from the bottom because, again, of this bridge. So after it opens, the oxygen ends up having a negative charge, and to fix that, we just do a quick H3O plus workup here. And this is a separate step because then it would make an acidic solution, and we don't want that. So yes, that's pretty much it. So this synthesis is how we get from this product, a reactant, to this product. And yeah, thank you so much.